All right, good morning, everyone. My name is Bertrand Irisu. I'm the CEO and co-founder of Brainome. It's my pleasure to welcome you to our fourth webinar on the benefits and applications of our measurement-based approach to machine learning. Before I get started, I just want to remind you that we have two concurrent webinar series. One is we call Core Tech, which really dives into the technical aspect of our measurements. And so if you want to know everything about the math behind and the science behind what we do. And then we have this particular series called the Benefits and Applications. We have a couple more webinars that will be coming up, but they're run on a weekly basis, although we will be taking a week off next week for the Thanksgiving week. If you'd like to sign up, please go to http://brainome.ai/resources/events. And if you have any question, please put them in the QA channel and we'll answer them at the end of the webinar. Our topic today is the benefits and applications. Oh, I'm sorry. The topic today is looking at, thank you, detecting and handling data drift in your data sets and your models. And it will be presented by Lynn Chase. Lynn is VP of Product Management at Brainome. Means she's been laser focused on making our Dimension users successful. She's earned her PhD in computer science at Carnegie Mellon in 1997, and she's been working on making AI software useful in the real world since then. She joined our team at Brainome a few months ago, bringing with her an extensive multi-decade track record of successful development and deployment of AI technology in business environments. So Lynn, without further ado, thank you.
Thank you, Bertrand. Well, we're going to be talking about data drift and how to detect it and how to react to it using the very powerful tools that Brainome's Daimensions software puts in your hands. And these are brand new measurement-based tools for supervised machine learning that bring all kinds of new capabilities to the game. So I'm very excited to be sharing these with you today. To get started, let's talk about what data drift is, how it happens, when it happens. And to do that, let's take a look at a very basic view of how a typical machine learning workflow works. So this is the state of the art, the state of how the field operates. The idea is that you start with a body of training data that you use to develop a machine learning model. And that data includes labels, which give you the ground truth, which is the reference for the supervised machine learning that goes on. And from that, you create a model. And then you deploy that model in an operational environment. First, you might test it in a lab kind of setting against some independent test data that you've got that reflects the same kind of distribution that you saw in the training data. And you will run that data through the model as a way to see how it's going to work when it gets deployed, and you're going to calculate some results. And typically those results are accuracy scores that are based on an error metric. And that's how evaluation is done for a model that was built using supervised machine learning. What happens when you deploy this model that's being applied in a real world environment is that the data may or may not end up looking like what you thought it was going to look like. And when it doesn't look like what you thought it was going to look like, we call that data drift. When the data that the deployed models are exposed to are deployed into a real operating environment, and the operating environment differs from what was expected, that's the notion of data drift. And when that happens, currently, prior to Brainome and the Daimensions software coming onto the scene, the only thing that was really available was doing accuracy measurements and trying to doing some kind of evaluation of what was going on with data drift based on accuracy scores. So data drift arises when the real world data does not look like the test data that was originally used. And the current approach involves building a model, deploying it live, sampling and labeling some live data, measuring accuracy for that sampled live data against the deployed model. And when the accuracy drops, when you notice that the accuracy seems to be dropping, revert to step one and do it all over again. That kind of looks like this. If you were to deploy a model and watch what was happening to the accuracy in the field, you would often end up seeing that a model that doesn't change decreases in its performance over time. And so what people typically have been doing is refreshing models on a periodic basis, sometimes just based on we know we have to do it every week, or we know we have to do it every 30 minutes, or we know we have to do it every month. And sometimes based on actually tracking accuracy and when things hit a threshold, redeploying a new model. Now, there are two basic problems with that kind of approach. Fundamentally, it's based on the idea that the only option you have is to build a new model and then remeasure accuracy. That's it. That's all you've got in the current state of the art. But building a new model in many cases is very time consuming and very expensive and even error prone. And then the second part of the problem is once you do have your new model built, you don't have visibility into what changed. You don't have a way to really truly understand what you were responding to. What was it about the combination of the operating environment and the model that you had deployed that was no longer working for you? So it's this combination of the double whammy of it's expensive to constantly have to rebuild and redeploy, especially when you've got essentially you're working blind because you don't really have any way other than that one accuracy figure to get any sense of what's going on with your model. So that is something that we really care about. And what we want to try to do at Brainome is improve upon today's situation. Today's situation is you can measure accuracy directly. You cannot measure generalization of a model directly using today's tools. Until Brainome came onto the scene, there was no real measure for generalization. There's just a way to look at accuracy on validation sets. There is a kind of a proxy that you can talk about using the approach that is sort of the state of the art today, and that is you can talk about how complex the model is that you've got deployed. But that's a kind of an unreliable way to measure anything because, in fact, in today's machine learning world, in the current state of the art, there's a very strong bias to build extremely large models as big as you can make them with as much data as you can get your hands on. There's definitely a more is better mentality. And so using model complexity as a proxy for what to do about data drift is not super useful given that very strong bias. So what can we do now that Brainome and Daimensions are on the scene? I want to encourage you, if you haven't seen the Core Tech series, to go over to our website, brainome.ai, and look at the archived webinars there, or join us live in December. We're rerunning those Core Tech webinars so that you can really understand what the math and the algorithms are behind these Daimensions measurements. For the presentation that I'm doing today, I'm assuming I'm going to give a quick overview of what these are, and I'm going to show you how they work in action. But I'm assuming that you've had a little bit of background on what they are, what these measurements are, that Daimensions brings to the table. So we've already said we're operating in a world where really the only thing we have is some kind of validation accuracy measurement. And so now we're going to add a whole bunch of new kinds of measurements to the toolkit. We can look before we even build a model in a measure-only mode. We can look at the expected number of parameters that we would need in order to build a neural network against a body of data, or the expected number of parameters that we would need in order to build a decision tree against a body of data. We can also look at something called the capacity progression, which I'll review quickly when we start to use it. But it's basically a very interesting learnability measure that tells you whether or not there's enough data in the data that you're looking at and trying to train from to gather what the rule is that best explains the data. There's also the generalization ratio, which is a measure, again, of how learnable the data is and how well you can do at pulling out rules from the data. And it's a direct measure of how robust a model is going to be against data that it hasn't seen yet. It's a very direct way to measure that kind of robustness against future experience. We also have attribute selection, and that is a very powerful tool that uses our measurements to figure out which of the data features, which of the data attributes have the strongest predictive power, have the most impact on producing both a highly accurate and a highly generalized model. And being able to pull attributes out and show which ones are actually going to be predictive is a very big part of how you can automatically detect and then respond to data drift using the Daimensions software. And then finally, before measurement, we can show you what the risk of overfit is likely to be. And then if you do end up building a model, which in many cases with Daimensions is very fast, very, very fast, then you can get an actual measurement of whether or not the overfit occurred during model construction. So anyway, that's just a quick run through of the kinds of measurements that are described in detail in our core webinar series, and which we'll be using to discuss how to detect and handle data drift in a world where you have a lot more tools now with Daimensions than you did before Brainome arrived on the scene. So in order to sort of show you how this all works, I'm going to dive right into a series of demonstrations. And we're going to start with a baseline, which is the Titanic data set. And what the Titanic data set is a passenger manifest of a subset of the passengers, 890 odd passengers of the 3,000 odd passengers who were actually on the Titanic. And it's got 11 features in the data. And those features range from things like name and ticket number to how many siblings, how many parents the passenger had on board, whether or not they were male or female, and what type of ticket they had, whether it was a first class, second class, third class ticket, what they paid for their ticket. Those are the kinds of features that are in the data set. And it is a binary classification task. And the classification is, did the passenger survive the tragedy or not? And so we're starting with the actual tragic occurrence as the baseline. And then in order to show you how detection and handling of data drift happens with Daimensions, we're going to look at 3 imaginary alternate worlds where the Titanic situation was increasingly more divergent from the original actual case. And we're doing this as a way to show, well, what happens if we deploy a model, and then what happens when the reality of what the data is that shows up to be processed by the model gradually diverges a little bit, and then more and more as we move along. And the alternate worlds that we're going to look like, the first one is not terribly different from the baseline. The first one is a data set where in this imagined operational environment, the same kinds of passengers show up as did originally, but it's a different sailing. And so the exact details of who the passengers are, it's all different. But it's essentially the same kind of scenario. So it's as if a similar sailing happened a week later, let's say. Then we're going to look at something that's a little bit more divergent. We're going to imagine a world where there is no such thing as first, second, or third class. Everybody is first class in our classless society. The passengers are roughly the same. All the other information is roughly the same. But in this case, there's no such thing as second or third class. So what happens? What happens to the performance of the model? What happens to what we can learn from using the Daimensions measurements? And then the third alternate world that we're going to look at is dramatically different. And it's a world in which all families are headed by females. There are essentially no male passengers on board. And in these female-led small families, there are mostly no children, but in some cases there's one child. And so that's a dramatic data drift. That's a big difference between the baseline and where we started. And so what I'd like to do is show you live what running on these different data sets looks like. And then we'll come back to the slides and I'll do a nice clean discussion of what the results really looked like. So if you get a little bit dizzy from watching what goes on with our demonstration here, don't worry about it. We are going to come back and take a nice organized look at the results. I think I might want to make this a little bit bigger. So bear with me for a second while I make this adjustment. My apologies. Here we go. That should be a little bit easier to read now. So what we're going to do is we're going to run, this is the command line version of the software. And we're going to just put in the baseline data, which is the actual manifest data from the 891 passengers that we discussed initially. And I'm going to run the software just completely vanilla, no parameters, no special configurations, no special requests of the software. This is just what would the software do out of the box. And while it's running, let me tell you, this is the command line version. This is what it looks like for our power users, for our enterprise users. There is, however, a very nice graphical user interface version of the software if you're just a beginner or if you're just getting warmed up with us, and you can use that for free if you go over to our website. And that is also covered and demonstrated in several of our other webinars. So I'll just do a quick run through, a quick reminder of what some of the outputs are and what they mean. We see the number of instances, which is what we expected, 891 passengers. The number of attributes is 11, and it's a binary classification. Passengers either survived or they didn't. And this 61.62% is the rate at which passengers did not survive from this list. And this is a smaller number that shows the percentage that did survive. Here's the capacity progression on this data. And what this is, I'll remind you, is a measure for how much data you need to see before you can actually learn the patterns in the data. This 8 is a reflection of how many parameters you would need in your model if you only looked at 10% of the data. This 9 is if you looked at 20% of the data. Then we move to 30 and 40 and 50% of the data. And then this 11 up, these pairs of 11 up here are for 80 and 90 and approaching 100% of the data. So you can go back to our previous webinars and see exactly what this is about and how this is calculated. But I'll just remind you that what you're really looking for here in the ideal case is that you get a little bit of growth at the beginning. You're learning more by looking at a higher percentage of the data, but then you're converging, you're flattening out. And in an absolutely ideal case, this would go 8, 9, 10, 10, 10, 10. But we do see a little bit of rise here at the end. Not a problem. Down here, you can see that we're being told that we're in the yellow zone, the mid zone, for whether or not there's enough data to generalize. So I'm comfortable with that. And then let's pop down here and take a look at what is the accuracy that just out of the box we're going to be able to get. It's a little bit shy of 80%. And our generalization right out of the box is 2.79 bits per bit, which is good. It's a reasonable performance. But I want to remind you, we can immediately do better and get more insight by adding the minus rank option. And what the minus rank option does is it asks the software to please tell us which of the data features actually have the most predictive power and to just build a model based on those. So what we're looking at here, and this is a very interesting part of the Titanic story, is the results of the attribute ranking. And very quickly, we were able to see that there are 4 of the 11 features that really matter. One is whether or not you're male or female. One is how big your family is, how many kids are in the family, and one is whether or not you have a spouse along. And then another very important predictor is whether or not you have a first, second, or third class ticket. And if you'll recall the story of the Titanic, you'll realize that this actually makes a lot of sense because there was a women and children first policy for those who got into the lifeboats. And it was absolutely the case that first class passengers got to the lifeboats before second and third class passengers did. So let's take a look at, once we did run with rank and we did identify which of the features of the data were most important in predicting outcomes, what happens to our model accuracy? Goes up a little bit, but really importantly, what happens to our generalization ratio? My goodness, that's gone up tremendously. So by paring down, by having the software find out for us what are the features that we want to use, we're able to build a much more robust model. And another thing to notice is that the model capacity, the memory equivalent capacity, which is essentially a direct measure of how big the model is tiny. This is a very, very small model because it's based on a very simple rule that got extracted from the data. And that's reflected in being carved down to a very specific set of attributes that do the predicting for us in this case. So again, the thing to take away here is that rank is a very important, using attribute ranking is a very important part of using dimensions. Now, that's just the baseline behavior. Let's take a look at what happens in terms of data drift, because after all, that's what we're here to talk about. So the first thing we're going to do is see what happens when we run the software, not on the original training data, but on a version of the data that's just a mild modification from our original world. And this is going to be a manifest of passengers that is very similar, maybe a sailing that happened maybe a week later, but just different people. So what happens here? Whoops. Sorry about that. My apologies. I must have had a typo there. There we go. And by the way, you'll notice that I'm using the minus FDT. I'm just saying it's very clear from the initial measurements that decision trees are the way to go. So we're going to ignore the neural nets for now. Well, look at that. It's very much the same as in the first case. We have the same capacity progression. We are working, the system has picked out the same 4 attributes that have the greatest predictive power. And that predictive power is very strong. We have a big generalization ratio, and we still have a very tiny model. So no big change there. Same set of passengers, different sailing a week later with similar kinds of people. So that's good. That's very much what we would want to see in terms of having tools for detecting data drift. Now let's take a look at what happens with our classless society, where what we're doing is saying there's no such thing as first, second, or third class. Everybody is first class. So what happens here? What do our measurements tell us when the world changes in that way? And what we see is that all of a sudden, ticket class is no longer an important attribute. That's very interesting. And our capacity progression, while it still has the same shape, the numbers inside of it are higher. So we're needing more model parameters to get to our final solution. And in fact, generalization is dropping off. It's still quite high, but it's considerably lower than it was. And in turn, the model capacity is starting to grow. So using these measurements, this is the one takeaway that I hope you get from this webinar. Using these measurements that were never available before in the machine learning world, we're able to see that data drift is happening. Let's take one last big step into a world where all the families are female run and they have very small numbers of children. Most families don't have children at all. Let's see what happens there. We're building a predictor for that. And let's take a look at the measurements that we get when we do that. Oh my goodness. So the whole basis for how the predictions are being done has changed. We're off to a new feature, which is called FAIR, which is a completely new basis for modeling who's going to survive and who isn't. So this has been significant data drift here. to see this massive change in what the attributes are that are now needed to try to do prediction. And the capacity progression has degraded tremendously. And in fact, along with that, we've seen a warning that says actually there's not enough data to generalize. We're now in a red zone. So warning, warning, danger zone here. And along with that, the generalization ratio has dropped dramatically and the model capacity has jumped to a much higher number. So I did promise you that you wouldn't have to remember all of that. And so let's take a look at what these results look like overall. This is just kind of a summary of what we just saw. So again, the baseline is the actual Titanic disaster for the 861 passengers that we were modeling. And then an imaginary future number 1, an imaginary future number 2, and an imaginary future number 3. Now, I told you what these imaginary futures are, but if you've forgotten the story, you can see that there's a progression from basically no drift to some drift to a lot of drift. Whatever the story is here for these imaginary alternative worlds, you can absolutely see based on the capacity progression and what's going on with the generalization measure and the learnability flag, which is a color-coded thing, and what are the attributes that are being used. You can see that the biggest difference here is in column number 3. The next biggest difference is in column number 2, and that there isn't much difference in column number 1. So if you're in a situation where these are the kinds of measurements that you have available to you, you're in a position to answer the question, do I need to retrain? Which is a really powerful new thing to be able to do. So you can detect whether data drift is happening, and if so, whether it's time to try to adjust for it and to react to it. So the answer is, in 2 of these cases, yes, you would need to retrain. Now, let's imagine also, by the way, I want to really emphasize, these are all things that you can measure without rebuilding a model. These are all measurements that you could make no matter what approach you're taking to building your model. They're all measurements that you can take to decide whether or not to invest in rebuilding. If you want to use dimensions to rebuild, you can. It's super fast. I just showed you some real-time examples of how fast things go. And if you do decide to rebuild, then you can actually get updated accuracy measurements as well. And you can also get actual model sizes for how big the model would have to be, and you can get the direct measurement of whether or not overfitting is occurring. So one thing I'd like to point out here is that let's imagine that you're operating in a fashion that looks like this, where you just go on a regular cadence and invest in retraining and redeploying your models. If you're doing that as your way of dealing with data drift, then you've got a way of knowing whether or not your accuracy is in the range that you want it to be in. But that's all you know. Without dimensions, you don't know why this is happening or what's going on underneath. You don't have any insights into what the nature of the data drift is. But in this case, you do. You have a way of saying, okay, I retrained here for the classless society and I retrained here for the female-led families, but all I really knew about them were that they were retraining points in my deployment cycle. I didn't know that it was because it was a classless society or because it was female-led families. But using dimensions and attribute selection, you can see what it is that's falling in and out of your model, and that gives you direct insight into what's changing in your world that's causing data drift. The other thing is, you might, in the case of extreme data drift, in this situation, retrain and think you're getting a good accuracy. But in fact, you're nowhere near strong a position with this model as you might think you are just based on accuracy alone. So these additional measures of whether or not the data is learnable, what the generalization ratios are, what the capacity progressions look like, whether or not you're seeing a tremendous rise in the size of the model, the memory equivalent capacity needed in order to achieve that accuracy. These are all very, very helpful insights to let you know, maybe I should go back. And in this case, if I saw these kinds of measurements coming out, I would take a serious look at trying to figure out what the new data features would need to be in order to get back to this kind of performance. So that's pretty much the story. Bottom line is Dimensions brings a lot of power to the game of detecting and responding to data drift, both because there are many, many useful measurements that can be done before you retrain a model, and also because if you do want to retrain models, it goes very, very fast. So that's the presentation for today.
Great. Thank you, Lynn. It was a really good presentation. Even I learned a few things along the way. I got a few questions in the Q&A section.
Sure.
Let me read them to you. First one is from John. John works on e-commerce data and is asking, are you saying that you can differentiate between a slow week and real user behavior change, like a pre-COVID, post-COVID world?
Yeah, I am saying that. Let's see, how can I answer that in terms of what we've got here? Let's say you were working on your baseline. You had your baseline model deployed, and some week came along, maybe the first week of September came along, and all of a sudden the accuracy dropped. If you ran the measurements and you saw that the attribute selection didn't change, the flag was still the color you expected it to be, your generalization ratio is still very high, your capacity progression still looks good. If all of those things are stable, then I'm going to say to you that what you saw was a change in who showed up for you that week, not so much a change in underlying market behaviors. So that could be, for instance, if you're in San Francisco and all of a sudden everybody goes to Burning Man. That's that kind of situation. It's not that people have changed on what they want to buy or how they want to buy or where they want to buy or where they want the market to go for the products that they're looking at from your e-commerce website point of view. It's just that they're all out in the desert doing something else. So I would say that those kinds of measurements, if they don't change, I would say hang in there for another week and then see what happens. That would be an option for you.
Okay. I hope that answers the questions. I have a second question from Brent. It is, my training cost is actually minimal. Why should I not just retrain instead of using measurements?
Well, you can, and that could easily, continue to work for you. I would say, if you're just kind of following this framework where you notice the accuracy drops or you just have a cadence on which you're retraining. But I would still argue that if you don't use measurements, you don't know why. You don't know why this model needs to be retrained, and that you could gain a lot of insight into, especially with attribute selection, you could gain a lot of insight into why does that model keep having to shift. And if I were a technology provider in an enterprise environment where I had business partners that I was trying to support with my machine learning capabilities, I would get a lot of points if I could tell them, hey, you know what? It looks like there's some kind of fundamental shift happening in people's reasoning and in people's reactions here because the attribute selection has changed dramatically in the following way. So I would think that that would be a benefit that you could get even if retraining is cheap for you.
Okay. I have last questions coming from Sulin, who's asking, how fast are measurements compared to doing a training?
Measurements are very fast, whether you compare them to doing training or not. I just showed you on in real time. You were here while we were doing measurements. So even on very, very large data sets that are much larger than this one, measurements are still super, super fast. Like you can just sit and watch them happen without getting frustrated. And then training of models using our software varies. Decision tree model training and some neural network training goes very fast, just like you saw here. In some cases, you might see an order of magnitude higher amount of time that it takes to build a neural network. But even if you're going with the neural networks, our training times are still really, really fast, almost 100 times faster than the industry average. So it's a fast tool.
Okay, that's great. And this is more coming from me this time around. Can you just comment on the size and number of features you can actually handle?
Oh, sure, yeah.
To go and look at data drift.
Absolutely. So we're super comfortable with very large data sets. The number of attributes can be tens of thousands, 100,000, and the number of lines can be millions. So very large data sets are fine. And those data sets can have mixed values in them. They can be a mix of floating point numbers and integers and text and character strings and whatever you want.
Great. Well, that's all the questions we have. Well, thank you very much for attending to this webinar. Just want to remind you, we do have a couple more in our series in the next 2 weeks. Actually, the first 2 weeks from now and then 3 weeks from now. We'll be taking a break over Thanksgiving. Feel free to sign up on our website and try our demo as well. And of course, we do have a parallel series of webinar on core tech, which are a little more technically oriented, and we encourage you to sign up. And if you have any questions, you can always reach us at support at brainome.ai. Thank you again for attending, and we'll see you all a couple weeks from today. Have a great Thanksgiving week. Thank you.